Hello, everyone. Thanks for coming. So I just would like to introduce what I'm going to demo today. So I'm from Codasip, and my role is actually the vice president of the university program as well as customer experience. So I actually have a multi-role within Codasip. So today I'm going to be talking about why RISC-V. I had a talk yesterday, the membership day with RISC 101 about why RISC-V. And so today I'm going to sort of follow up on the same theme, and it's all about customization, because some of the big markets for RISC-V and in some of the keynote speakers, we heard about IoT, the edge, and DSP. What makes them unique is each one of these applications have a unique need, and therefore some customizations. So today I'm going to do a live demo. So they give me a full hour, so I'll go as fast or slow as you want. And after I finish, if you want to ask me to do some more customization, I'll do it live with you guys as well. So first of all, let's take a look at architecting your ambition through performance enhancements. So, if you look at application time, or how fast your application works, basically it's a simple equation. The number of instructions you have to execute times the average number of cycles per instruction, and then over your CPU frequency. So that's the basic, algorithm or equation. So we're going to use this equation to actually modify a core that actually does the following. First, I will show you how to reduce the total number of instructions. And what we're going to do is look at a profile. And so we're going to collapse 2 instructions into 1 instruction. And therefore, when it reduces the total of instructions, and you can see that the number of cycles will be reduced. Second thing I'm going to do is, the second part of the numerator is average cycles per instruction. So I'm going to show you how you can change the microarchitecture to actually reduce the number of your cycles per instruction, which once again reduces the total number of instructions. Then I'm going to do a little bit more of a complex addition, which I'm going to add a new compute element. So we're going to take a core and add another compute resource, which will actually reduce both the total number of instructions and the average cycle of instructions. And then I'm going to do a third one, which is I'm going to add an additional resource. And therefore, when I add additional resource, I can have a more complex instruction, which once again will reduce the total number of instructions and my average cycles per instruction. So a fairly well set up sequence. And I apologize, I used to teach at the University of Colorado. So I, sometimes go into professor mode. So we're going to go through this today. And let me switch over to Codasip Studio. So the first thing we're going to do is, I'll let you know what I'm using is Codasip, since I'm the university program. What we do is actually offer a set of curriculum that professors can use as project-based learning in their assignments. And so we provide access to our software, all to the curriculum, also rubrics and other material, all free to help the students in the universities. So I'm going to use the core that I used, and these are some of the same assignments that the students will actually implement in their class. So what we're going to do is take a look at bubble sort. It's an application that a lot of students know about. They might have done it in their Computer Science 101 class. So we're going to look at how to accelerate that. And so the first thing we're going to do is take a look at a profile. So within Codasip Studio, you can actually execute your program in what we call profile mode. And when we do profile mode, it gathers statistics of your program. And then we're going to analyze that. And from that, figure out how to collapse 2 instructions into 1. And therefore, I'm going to improve the performance of the processor. Now, if I scroll down here in the instruction set coverage, I can actually go and see, is there a sequence of instructions that are occurring, and can they actually be replaced with a single instruction? So we're going to take a look at that. So if I scroll down here, I take a look at this particular instruction right here. I don't know if I can walk to show it there, but hopefully I won't get feedback, but this one right here. Since I know this core, this particular instruction, I have the hardware resources to collapse these two instructions into one. Now, if you look at the first instruction, it's a subtraction. If you think I have 0 minus another register, so I'm really taking the negative of a value. And we see the DF0, that means it's the same register number. So I'm using the same register number. I'm taking the negative of a register, storing it in the same register. And the next instruction, what I'm doing is I'm ANDing it with a different register and then storing it back into the original register. So what I'm doing is sort of like a mask type of operation. So it might be tough to see, but on to the far right of that, it happens like 5.1% of all instructions. So if I can collapse those two into one, I should save about 5.1 number of cycles, right? Because now the 5.1% of the time, instead of 2 instructions, I'm going to do 1. It might not be exactly the same because now the compiler might start rearranging the code somewhat. So I'm going to show you how to do this live. So we're going to switch over to what we call our Codasip Studio view, which is really the more design environment view. And the first thing we're going to do is actually add the instruction in our instruction accurate model. So the nice thing about this our tool is if you define a new instruction, the compiler will pick it up, and then we'll use it every time you actually compile. So I need to tell the first thing I need to do is I need to go and include an opcode for this new instruction. You know, what I would do if I was doing this for work, I would actually go look for a custom opcode space and be a little bit more diligent on what the opcode is. But for speed, what I'm going to do is just I know my operation is going to be an R-type, so I'm just going to create an R-type instruction. So I'm going to come here and I'm going to say R-type. It's a mask type of operation. I'm going to say R-type mask. And right above this is, you can see these are all my different R-type operands. So opcode. So it's really easy for me to see what is going to be a unique opcode. So I'm going to go 11101. And the last 7 digits is important because that's the opcode for R-type. It's the lower 7 bits. So now I've actually defined the opcode, right? So now I have to add it into my instruction accurate model for my compiler. So to do that, I have to go and tell my ISA, my instruction set for my computer. And once again, this is my program that the university students use, so it sometimes has a little bit more comments than I would normally have in my production code, but it's not bad to have comments. So the first thing I need to do is add the opcode as an element. So I'm going to say mask, R-type, mask. So now I've actually created this instruction element called a mask using an opcode from R-type mask. And now I'm going to have to include it into my set of opcodes for the R-type element. So I say set OPC R-type ALU plus equal OPC mask. So now I've just added into my set of all my R-types. Now, if you look down here, you can see that as I define my R-type, I'm showing what it looks like in assembly language, as well as what it looks like in a machine code. And since I'm not creating a brand new type of instruction, I don't have to retype that in because it's already an R-type instruction. So I'm going to scroll down here, and you can see where I've added, or the previous R-types, add, subtraction, so forth. So I normally tell my students never cut and paste, because it's easy to make an error. But I'm going to be really careful, and hopefully I won't make an error. So I just added this one here. I'm going to say mask. Now, if you remember, it was the first operand ANDed with the negative of the second operand, right? So I have to define exactly what I want right here. So I'm going to say and subtraction, right? Because that's what the combination of the subtraction and the and immediately following it. So that's all you have to do to add a new instruction into our tool. You create an opcode, and if you already have an instruction type, you just add it in as one of your semantics of your switch statement. Now, what we're going to do is I'm going to start building the SDK here. Now, if you look at the SDK on the tools on the right, it's sort of like a big makefile. So it's going to look at everything above it, and if it needs to rebuild it, we'll rebuild it. So it's going to build the assembler, the disassembler, the profiler, the debugger, but the more important thing is the C library and the C compiler. So when I finish this here, which will take about, on this particular computer, it takes about 2.5 minutes, I will have a C compiler that will understand my new instruction. So as it's going to do that, I'm going to now implement that into the cycle accurate model. So from the cycle accurate model, I can now generate the Verilog or the system Verilog to generate the RTL out to actually be used in synthesis. So anytime you add a cycle accurate function, there's basically 3 things that you normally have to do. The first thing I'm going to have to go, if I'm reusing a compute element, this time an ALU, I have to create a microcode opcode to that ALU that says, okay, I'm going to do a mask operation. So if you notice, it's just the enum. And so I'm just going to come down here and say, I'm going to define a new enum, ALU mask. And so now I've created a new micro opcode. Now, what's really nice about this language is the way it's set up. As I add more enums, it will actually change the bit width automatically of my micro opcode. So I don't actually have to go to any signal and say, okay, now I have to use, say, for example, 6 bits instead of 5. It will do it automatically for me. So first of all, I created my micro opcode. The next thing, I have to go to my decoder, and I'm going to go find my R types. So here's my R type, and once again, I'm going to be really careful with my copy and paste. And so I'm going to do mask. And I'm going to do mask here. So now I'm using, every time the R type sees the opcode of like mask, it's going to now call my micro opcode to my ALU to do a mask. So then I'm going to save that. And the third thing I have to do is come down and actually add it to my ALU. And I come down to my ALU here. Here's an AND, so it's very similar to an AND. So cut and paste. Now I'm going to say the micro opcode is mask. And I got to make sure that what I tell the ALU is exactly what I told the semantics for the instruction set. So it's going to be and minus. So they have to match. So I've actually now finished the cycle accurate model. So this will actually generate the RTL that you need to actually run your code. The one thing I forgot to point out, I think the number of operations was like either 3.4 or 34 point something number of total cycles. So we'll look at that in a minute. But now I've just generated the IA model, because you can see down here that it's complete. You can see it's completed down here, as well as if you look at the task here, it's all completed, my SDK, right? Now, yes?
Runtime library. Will the compiler pick up your new instruction in those libraries as well?
Yes, so it always does the compiler first, then the runtime libraries, yes. Yep. So now to show you that I'm using my new instruction, if I didn't make a mistake, is I'm going to go to the bubble sort, and I'm going to say clean it so I can make sure that I rebuild it with the new model. And I'm going to say build. So it gets built, so I just recompiled. Now I'm going to go and take a look at the, first of all, I'm going to look at the disassembly. Oops, double click. And my new instruction was called mask. There it is. Right, so if let's see, is this in the library? Just trying to see if this is in the library or not. To actually show you proof of that, right? Where's the top of this function? What's that? Did I miss it? Yeah, it's a part of a function. So right there, it proves to you exactly what you want. So now you can see that the compiler actually took my new instruction and it's in the library, which now I'm going to add this to my demo. And it will always be used anytime you use this library. Now, what I'm going to do is now reprofile it. Well, first of all, I need to rebuild the cycle accurate model. So the cycle accurate model will actually build quicker than the IA model. I didn't really point it out because I was sort of talking about how to implement the CA model, but there's like 1,000, it's over 1,000 libraries that it has to build. I only have to rebuild that when I do the IA model. So I don't have to rebuild that in the CA model. And so that is one major reason why the CA builds much quicker. So now I'm going to rebuild the CA model. It will take me on this particular computer around a minute to worst case a minute and a half. I have to say at home I have a machine that I built. So the way the code works, it wants to parallelize its effort. So the more threads you have, the faster it is. So my machine that I have at home, I had purposely built. It has 20 threads, so it really does go much faster. But this machine still, it's a notebook, right? It's not really designed, but you can see that I'm finished with the CA model. Now, I'm going back to my profile here, and I'm just I just ran the profiler. And it's going to calculate the results and display it in a graphic image here. But to go back, I'm going to take a look at, oops. Let's see. The issue of doing a demo.
Intel processor or AMD processor?
It's an Intel processor. I have to say, I do like my home computer a lot better. It's so my son got me into building my own computers, and so well, I should say I started my career designing workstations, so it's somewhat in my pedigree. Now, if I come switch here, I just want to show you. I've added a few pieces of information here. And you can see down here where it's calculating the number of cycles executed, the number of instructions, cycles. And this is just from the standard RISC-V CSRs, status registers. And it calculates the cycles per instruction. So this is the IA model. So the IA model is defined to be any instruction will take 1 clock cycle. So it should be 1-1. So you can see that in the IA model, I have a CPI of 1, and it used to be 7 something, or up here, cycles, total cycles I mentioned before that I should have showed it to you before was like, should have been like 3.4 million cycles. Now we're at 3.28 million. So if I calculate that out, that should be roughly somewhere between a 4 to 5% improvement in performance. Now if I come down here, and I look at, oops, I'm going to just say type in mask. And you can see that it used it 5.4% of the time, right? So you can see that I've actually taken those two and collapsed it, and it becomes 1. Now, let's take a look at, now I'm going to say, let's profile it, but I'm going to profile it with the CA model instead. So I want to actually take a look at what does the cycle accurate model look like. Because remember, there's two parts of the numerator: total number of instructions, and then also the average cycles per instruction. So I got both that I need to worry about if I'm actually designing or optimizing my core. So you can see in the window here that I'm running the simulation here. I'm profiling it, and now it's going to display some information. But the key thing that I'm going to show you is the actual cycles per instruction average. Because the next part of the demo is I want to show you how to reduce your CPI, because the top numerator of the equation is total number of instructions, and then can I do anything with my microcode to make it run faster? So if I come back to take a look at my CPI, you can see that my average cycle per instruction is 1.25. Now, my core for my student curriculum is the standard 5-stage core that you would see in David Patterson and John Hennessy's textbook, right? So the basic core has no branch prediction. So if I do my branch in the memory stage, every time I have a successful branch, I have to flush out 3 previous stages, right? So every time I do a branch, it will increase my average CPI because I have to get rid of some instructions that are already in my core. So what we're going to do is just a simple branch prediction. It's so simple. All we're going to do is every time I have a jump, and I can determine that in the decode stage, I'm going to do a jump in the decode stage and not wait till the memory stage. The nice thing about the jumps are they're non-conditional. So, and what's also about the JAL instruction is I don't need to have any information. The jump is the RPC, the program counter, plus an immediate, right? So I don't even need to ensure that the register file is up to date, right? Because I'm not even using the register file. So it's a really easy thing to show in class, and I'll show it here right now. So what I'm going to do is actually go back to my equation and reduce the total CPI by affecting the microarchitecture. So I'm going to come here and go back to my Codal view because this is the main view that you do your editing. And so I'm going to add myself a couple of resources here, and basically, you can almost consider this as like I'm adding, it's basically, we call it Codal, but it's really C type. So just assume that when I add something here, it's almost like a global variable. Even though in my embedded software class, I tell students you never are supposed to use a global variable, but we're going to create a signal which will be global. And what we're going to do is have 1 bit. This is a definition for 1 bit. I just created a definition for Boolean bit. And we're going to call it, so we're going to call it SID for signal in the ID stage, JAL predict. Now I'm also going to create another signal because I have to calculate my jump address and implement my address when I actually see it. So I'm going to say signal bit, and I have something defined as address type, which is 32 bits, unsigned. And that's also a signal. I'm just going to call it JAL target. So for the simple branch prediction, that's all I need to do. So now I'm going to go back to my decode. You can see down here I have each of my stages specified on the leftmost column. Open up my decode, and I have to make sure that I've parsed my instruction. So I'm going to take a look at after I parse my instruction, because part of the parsing my instruction is I'm actually determining the JAL immediate. So you can see up here where I've created all my immediates, my R type, I type, S type, B, U, and J type of immediates. So my first thing I'm going to do here is I'll do it like right before my decode. I'm going to say SID JAL target equals IF ID PC, and let me make sure I get this right. Let's see. My J type. So that's my equation for my target. I got my J type immediate plus my PC. Now, I use a particular nomenclature, and I like to talk about this nomenclature once again with my students. Is R means it's registered instead of a signal. Signal is combinatorial, it's just a wire. And then ID for all my signals will actually specify the stage that the signal is generated or located in. And for my registers, IFID means it came from the iFetch stage and it's going to go to the decode stage. So now so the RIFID PC is actually the PC address of the JType or the JAL instruction. So now I'm going to have to go and tell it that if I actually see something that's a JAL, to actually jump there. So you can see I have this simple equation, and you can see my first line is if I have a branch, go to the branch target. Well, since a branch is decided in the memory stage, it's an earlier instruction than the JType in the decode stage. So I have to prioritize that. So which means that I'm not going to put my new branch prediction ahead of my my signal from my memory stage, but I'm going to create an else if. Let's see, it was ID JAL predict. SIF next PC equals ID JAL target. So if hopefully I typed everything correctly there. Let me save that. And you can see that I did because it's all the color indicates that it's a known signal or register. So now I have one thing left, right? I created a target, and I say that if I predict, I'm going to see it. So what I'm going to do is go to the decoder for the JAL. Let's see, JAL. And so this is my JAL. And if I have my JAL, I'm going to say, let me go down here. Let's see, ID JAL predict equals true, which means that every time I decode that in the decode stage, I'm going to say, just do an early branch, right? Because it's an unconditional branch. I don't have to compare anything. It's an unconditional branch. So I'm going to make these false because I'm not going to do a branch or a jump now in the memory stage. So now I've actually made all the changes necessary to actually do a unconditional jump in the decode stage. Now I'm going to now build it. So if you notice over on my over here, where the IA model is still built, you can see the CA model is no longer built because I've modified that. It's just a big make file. It's just a visual version of a make file, right? So since I didn't change anything that would affect my IA model, my IA model is still valid. So all I need to do is come back here and rebuild my CA. So this is going to take me, or like I say, another, oops, I had a error. It's the problem when you work on a work project which has different nomenclatures a little bit. So there we go. So if you notice that when you have an error message, it actually has a hyperlink exactly where the error message is. So that's really good. So the one thing that I found, so I've been using Codasip Studio for 7 years now because I brought it in at the University of Colorado. If you take the computer architecture classes there, they actually design a 5-stage RISC-V processor in their course. And they actually, after they finish building a 5-stage processor that actually runs C programs, the next thing they do is the next 2 steps that I will show you. They will actually learn how to they will learn how to add an instruction, which we have already done, and then they will also learn how to actually change the microcode to do a branch prediction algorithm, not just an unforced or a unconditional jump. So we're getting close to being finished here. So there we go. So let me I'm just going to run it here. Just it's a little quicker since I don't have to do the graphics. So now you can see that my CPI went down to 1.14. Where is it easier to show here? Well, it was 1.125, right? So I've just showed you how you can actually take a look through the profiler and you can learn several different things, how I can reduce the total number of instructions by collapsing 2 into 1, and then how to modify your microcode to actually reduce your CPI. Those are the two numerators in your equation, so your application is going higher performance. Now, before I go to the next step, one professor went on a conference, so he asked me, it was our sophomore Verilog class, can you take over my class for one day because I'm out of town? And I said, no problem at all. And I go, what should I do for your class? And he said, just show them what they would do in your class, which is the junior level computer architecture class. So in that class, I actually go through and show them how to do a demo where we actually do the same thing, but we actually add a multiply accumulate instruction. And at the end of the class, since they're learning Verilog, I decided I can't leave without showing them Verilog. So I go, okay, there's this little task down here. It's called RTL. I click on it, and it's now done. So the Verilog took 5.5 seconds to do all the Verilog, right? So the students, then when the professor came back, I asked the students, how did they like my class? And they said, well, they really liked it. They were wondering why are we learning Verilog now, right? Because they like C, they understand C. Verilog is a lot different, and now you have this program that actually generates your Verilog for you. And the Verilog is highlighted, so if you actually look at the RTL, which afterwards, if we want, I can show you, it's all commented out. It actually shows exactly which file and which line that particular Verilog, or if you want system Verilog or VHDL, exactly where it came from. So it's very easy to go back. So now I just did the first two parts of my demo. And now the next part is, okay, this is, if you remember if you are familiar with the David Patterson, John Hennessy book and the 5-stage pipeline, it just has an ALU, no multiplier, right? And so what we're going to do is, let's take a look at CoreMark. That's a very common industry benchmark. So I'm going to go to CoreMark here. And I'm going to just make sure, let's say I'm going to say clean. I'm just going to make sure it's built with my current model that I have here. So I'm building up CoreMark. And I'm going to actually run CoreMark now. Let's see, run CoreMark. CoreMark, I run enough iterations that it takes a little bit of time to complete, but not too long, maybe about 15 seconds, I think. Now, let's see. Now, it should be almost ready. And after adding the compute resource in a minute, it will go faster. But you can see here that my CPI is 1.22, and the total number of instructions was 73 million, right? So I know enough about CoreMark that it likes to do multiplies, right? And the basic model from David Patterson, John Hennessy's book doesn't have a multiply. It's just an ALU, an add, and so forth. So what we're going to do is actually add a new compute element. In theory, I could add it to the ALU, but I want to show a little bit more of what you could do by adding a complete new element. So first of all, I have to tell the compiler that I have a multiply. So let's go back to what we did. The first step is add a multiply to it. Now, we're going to go back to the my opcode. And just want to let you know, you can see that I've already added my opcode for multiplier. So I've added that here. Now I have to go into my ISA. And similar to what I did with the mask, I have to add an opcode, my multiply. I'll call it mul, and multiply. Now I have to add it to my set. So I just did it just like I did before, right? Now, I'm going to do the exact thing I did before. I'm going to do cut and paste, but very, very careful that I don't make a mistake. But now, instead of and minus, I'm just going to do multiply. Now, when I compile, now I have a multiplier in my compiler and in my C libraries. So I'm going to go and rebuild my IA model. But now, once again, I could somewhat add a multiply in the ALU, but it should be its own compute element. So I'm going to actually show you how to add the compute element. Now, I got to go back because I need a few additional resources. But first of all, let's go in my define, and I'm going to actually create a new enum. Like you can see up here, I have an enum for my ALU microops. I'm going to do an enum for my multiply. And you don't have to do this, but I always like to have a no-op for each compute element, but you don't have to. So now I've got a microcode that I've started developing for my multiply unit. So this is what I was mentioning before. We have this structure up here, and you can see bit size, right? So I want to just go here and so what I'm going to do here is create a definition that will determine the number of signals required to go to my multiply compute element. Now I have two microcode elements or instructions that go to my compute element now, a no-op and a mul. So really I only need one signal right now. But if I all of a sudden add to support of the upper 64 bits, that would be a different opcode, and then all of a sudden I would need two. Now we're going to write this code that so as I add more micro opcodes to this compute element, I don't have to go back and automatically change the number of the width of my signal. We'll do it automatically. So you can see I've created this new definition, mul op, and I'm going to have to say tell it what to do the ops sizing with. Now I'm going to go to my my resource, and I needed a few additional resources. So the first one is I need something that when I actually decode multiplier will actually send the microcode to my next stage. So I'm going to say my mul op w so because I don't know the width of my multiply micro opcode right now, even though I know it's 1, I just don't want to rely on that. So you can see I've just added something with my multiply, right? Now I've let's see, I've actually decoded this operation in the ID stage, so I have to pass it into the execute stage. So I need to pass it through the pipeline. So I need to actually this time add a register. So register bit, oops, mul op w. So R for register. Now I'm going from IDEX stage, mul op. But now I'm going to define it as a register, a pipeline register. And it's really important that I do this because if there is a branch, I need to make sure that if I have a branch, I have to flush out a multiply if the branch occurred in the memory stage and I'm transporting something into the execute stage. And that is the reason why I created the first multiply operand as no-op. Because when I clear my pipeline register, everything will become 0. So I really want my operation of my multiplier not to occur if that ever becomes 0. So I have pipeline equals, and I have to tell which pipeline it belongs to. Let's see, that'd be IDEX. So now I've created all my resources that I need. So if you think I'm following a very similar set of steps that I did, but I've added a few different types of resources because I'm adding something more complex. Now, I have my resources I need. Now let's implement it into the circuitry. So the first thing I need to go back to the decoder. And let's go find my R types. And let's see my R type. So I'm going to do cut and paste again. I'm going to be very careful. So one thing I want to point out here, and I typed it this way for specifically, is if you notice for my multiply, I'm actually telling my ALU to be a no-op, right? And I'm telling my multiply, if I have a multiply, do a multiply opcode. But if you notice, I'm not going to any other location and saying multiply no-op, right? And I don't actually need to do ALU no-op here. So the way the program to make this easy for you, everything in the decode stage is default as false or not to occur unless I specifically say to do it. So it makes it just easier. Like I can add the multiply, and now I don't have to go back to all my other instructions and say multiply equals no-op. I only have to tell where I want to have a multiply. So now I have it in the decoder. Now let's go back to the ID stage, because I'm going to have to pass it into the execute stage. So, the way I like to structure the code with students, because I think, code should be structured well. I have a, let's see, where's my stage here? I have an output event, or it's called function call in the ID stage. And so I'm just going to add it in, and it doesn't really matter where I add it, so I'm just going to add it here. Let's see, it's IDEX mul op equals SID mul op. So now I'm telling it that I want to include the decoded multiply operation to be transferred across the pipeline register into the execute stage. So we're getting close to finish now because we've created the resources, we've actually generated or decoded it, and now the next thing is to actually to add a new compute element. Now to add a new compute element, I'm just going to find a space down here. Oops, let's find a, let's see, get to the execute. So I'm just going to say event, let's call it multiply. And this resource is located in the pipeline of the, from the EX, it's in the pipe stage called EX mem. And so I'm going to just add it, oops, right here. Thank you. Oops. There you go. Yeah, thanks. Thank you. I didn't notice that one. I looked at the missing the close param. So now I've actually created the structure for a new compute element. Now, if you look at it, it's very similar to like adding an instruction. There's a semantics, right? So I have to do a semantics. So I'm going to say semantics. Semantics. Is it the, yeah, S. And if I fully build out this multiply compute element, I'm going to have, for the RISC-V ZMUL or M extension, I need 4 multiply opcodes. I'm only going to implement one for this demo, but I'm going to just know that I'm going to implement more in the future. So I'm going to actually use a switch statement like I did for my ALU. So switch, let's see, that was R IDEX mul op. And my first, oops, case is, well, it was R, oops, R type mul, no, excuse me, my opcode, mul, Right? So I got to fill that in, right? Oh, actually, I do need one more resource. Let's go back to this. So I need a resource in my execute stage that has my result. So signal bit, let's see, word W, SEX, full result. Because I have to actually have a separate, since I have a new compute element, I have to have another set of signals to actually put that compute element or result. So let's go back to my execute stage. And so EX mul result equals, if you notice my operands up here, I'll just copy one here just so I can make sure I type it in correctly. Times, and that's my multiply, right? I got my operand 1 and operand 2. It's a standard R type, so I didn't have to change anything because it's just going to take the right from the register file, source 1 and source 2. Now, if you think of it, I've got, I'm all the way, and I got a multiply result. But now I actually have to get it to the point where it will go into the memory stage, into the write back stage. So I need to do a little bit more, and then we're ready to actually try it out. So let's go to my output of my EX stage. And you can see that I have this particular signal right now, right? That actually is taking my ALU result and putting it into the register to go to the next pipeline stage. So now we're going to make this a 2-to-1 mux, which you can do via a switch statement, or I'm going to actually do this through a trinary equation. So let's see, the EX, let's see, ID EX mul op not equal to mul nop. If I do that, I'm going to put the multiply result onto that bus. So now what I wrote up here is if the opcode for a multiply is actually entering the EX stage, I'm going to use the multiply result to go to the memory stage, which will then go to the write back stage. So almost finished, because what I really need to do is tell the execute stage to actually call the multiply unit when it's time to call it, which is really simple. And, you know, I basically have to say for my, you can see this is my main event for the execute stage, EX. I have to say that, okay, you want to use the multiplier event or resource. Let's see, I think it must be multiply. Let's see. Okay, so I can actually make sure I got the right name because I could see it actually change colors. So in my execute, you know, I just have to say that check the multiplier. Right, and you can see my multiply is there. Multiply. And it's down here is multiply. So now I've added all the resources. Now, I've been standing up here, so I hope I typed everything correct. So let's see it. So I'm going to click on STK, so we'll build it. So let's see, were we at like 73 million instructions, something like that? I forgot how many millions instructions. It was something like 73 million when I had no multiply, right? So we're going to actually run it again here and see how many it takes now. It should be significantly less because now my multiply, as I defined it here, is going to tell the RTL to generate a single, parallel multiplier. So we'll execute the multiply in one cycle. Now, if you wanted to get a little bit lower in the microarchitecture and not consume as much area, you could actually define a serial multiplier. So that would reduce the area, but then you'd have to have a little state machine that says how many cycles it takes to complete the multiply. But for this demo, I'm just going to do a very simple parallel multiplier. because the real idea here is I just want to show you how you can add another compute element. Now you can see that I got the CA model done, right? And now I'm going to run the core marks. Now I have to actually rebuild my core mark program because I did change my compiler to understand a multiply instruction. So I'm going to go to core mark, clean it, and build it. And let's see, go to core mark, disassemble it. So you can see that my compiler now is recognizing the multiply, right? Just like I did when I did the mask operation, right? So now we're going to run it, and hopefully I got the CA model right. It should take less time because that's why I added a multiplier, right? A multiply compute element. So it will take, 15 minutes or so. Oh, that's much faster. So you can see how the compute element, now you can see that I'm down, instead of like 75 million, I am now down to 30, right? So this is showing you, once again, the power of the tool. And one of my things that at the RISC 101 meeting yesterday, I talked, one of the powers of RISC-V is you can start with a base core, which is a little less performance than you really need, and then you can build up to the resources that you need, right? And the advantage of that is you're not going to pay what I call IP leftovers. Now, if you take your requirement and just say your requirement is 100, and you go to what I call the processor grocery store, the odds are you're not going to find a processor that has 100, right? Some are going to be 50, 60, 90, maybe 150, 200, maybe even 1,000, for the HPC cores. But you only need 100. So if I bought 150, that core has more resources than I need, which means I'm going to spend more on royalties, more on licensing, more on current and power and energy. Now, if I took the core that was 80 or 90 and added my custom instructions or added a new resource, I can get right up to 100 or slightly more and actually just get what I need, and I only pay for what I need in terms of all those different characteristics. Now, when we talk about, you go, okay, what's the big difference if I have to pay an extra, even $1, because my application is so fantastic, an extra $1, I don't care. But now you might say that, not realize that, okay, well, mine's battery powered. And now, because I didn't use the right size core, my battery only lasts, say, 8 hours, but my marketing tells me I need 10 hours, right? And then you fail, right? So when you look at customization, it's not just always the cost of the core, but you're looking at optimizing energy and everything else. So that is my third part of my demo. And my next part of the demo, I feel like a magician right now. So my fourth part of the demo is, okay, we showed compressing instructions or collapsing instructions. We showed how to change the microarchitecture to reduce the number of CPI, showed how to add number of compute elements. Now, what happens if you want a new type of an instruction? And we're going to do a MAC instruction, a multiply accumulate. Now, if you think of multiply accumulate, I have 3 source operands. My two operands will do my multiply, and then my third, which is my accumulator, right? And then, of course, I'm going to assume my accumulator is also my result register. Now, the nice thing about, if you once again go back to the basic core here of what I did, the basic 5-stage pipeline for David Patterson and John Hennessy is a register file of 2 inputs and 1 output, 2 reads and 1 write. So I can't do a MAC right now unless I make a multi-cycle MAC. But I really want my machine to go even faster, so I want a single cycle MAC. So I'm going to have to add some resources. So I'm going to go back to my design, and I got my IA model, and I have this file called architecture. So if I look at my architecture, you can see that I have a, so I think it's better with the mic over here. You can see my data ports. I have source 1, source 2, two source inputs, and I have one write. So I need to add another source input out of my register file. So now I have 3 read ports and 1 write port. So I come here, and I'm going to do source 3, my third source, right? And let's see, let's go to so I got that. So now I have to create a opcode. Let's see, opcode. Just for simplicity, I'm going to make it look very similar to my multiply opcode. And I'm going to call it a MAC. And make it different. Let's see, just make it 1, 1. So now I've created it. Like I say, if I was really doing this for work, I would actually look at a custom instruction, because a MAC is a custom instruction in RISC-V, and create my own based upon the definition of RISC-V custom instructions. So now I've just created my opcode for my MAC. Now this is going to, I got to do a little bit more work now to add a MAC to my IA model, because it's not truly an R type, right? Because I have 3 source operands and 1 destination operand. So I got to go back to my ISA model, and let me find a good something to, let's see, this looks like a pretty good one to cut and paste. Let's see, we're going to do a cut and, oops. Let's see, cut and paste here. And okay, I'm going to do a cut and paste. And I'm going to change this element and say it's going to be a MAC element, right? And I got to create my element here. Oops, DBC, DEF, OPC, MAC, MAC, R type, MAC. I think I spelled that all correct. And if I was doing this for work, which I've done a MAC for work, I normally have more than one type of MAC operation. So I'm going to create a set here. Set I R type MAC equals OPC MAC. So I've created my first MAC operand in my set. I have to change my OPC to MAC. Let's see, did I type that right? OPC. And I'm actually need RS2 and RD. So I got my 2 source registers, right, and RD. I don't need an immediate operation. Oops, I don't need immediate operation. And my MAC is OPC, and then I'm going to have my RD, RS1, and RS2. So that's what my assembly language is going to look like, right? Now, to make sure I don't mistype, I'm just going to use an opcode that looks very similar or exactly like the R type. So I'm just going to cut and paste. I always do this in front of my students, even though I told them never to cut and paste. Let's see. So now, if you notice, I have a binary that has 2 source registers and an RD register. And normally for what I like to say, instead of just use RD, I'm going to do RD and say it's RDRS3. So you can see that it means both. So it's not just RD, it's not just source, but it's actually going to be both a source and a destination. So I have to come to the binary and basically say the same thing so that it matches up there. So I'm getting really pretty close to actually finish my IA model by adding a new resource and a completely new different type of instruction. So now I come down here and I'm going to, well, this is where I write the model, my result into the register file, and I know it's now called RDRS3. Now, if you remember, I don't have an immediate, but I do have a source, a source 2 and a source 3, right? Because I have 3 sources. And so I'm going to say, you can see here where I define source 1. And now I'm going to do source 2. And this is RDRS3. And, oops, 2, 3. And I don't have an immediate, so we'll get rid of that. So now you can see that I'm actually reading 3 from all 3 of my ports at my register file. Now, I only have 1 currently Mac, but we'll keep the same, assuming that I'm going to create more Mac instructions. And that is going to be, so for my Mac, I have my result equals SRC1. Let's see, let's do it right. SRC1 times SRC2 plus SRC3, right? So that's basically what my Mac operation is doing, right? It's creating a result, and I'm going to save it into the same register that I actually read my accumulate from, right? So this should be doing my Mac operation if I typed everything correctly again. So I should be good to go if I got everything correct. And so let's start building the IA model. And if I mistype something, I should get a warning pretty. Oh, I know. I've got to tell it to add the element ISA plus equals let's see, IR type Mac. And let's see. And remember, I was calling it RDRS3, right? Once again, it's very helpful. The error message take you right to where you need to go. The nice thing about this, let's see what other error. Oops. Let's see, ISA, R type, element, IR type Mac, IR, let's see. Let's see, what did I do wrong in my element? What's that? Oh, yes, thank you very much. Thanks, Carl. No, thank you very much. That's a similar reason why I don't like cut and paste, because when you cut and paste, you think something is correct, even though it's minor, and you don't always change everything correctly. Thank you very much. So now I'm compiling my IA model. So I just showed you an example where I'm actually adding resources. And so as we build this, I'm going to actually start to reuse those resources in my CA model. So now if you think of it, in my CA model, well, I don't know if I have time to do the CA model, because in the CA model, I actually have to also add data hazard and forwarding detection, because I have 3 input operands. That I could do that, but it's a little bit tricky, and it probably will take me about 10 or 15 minutes to do. So I'll just show you in the IA model that you can actually add this resource. And then I'll take questions, and then if everyone wants me to do it, then I will do it. add the data hazard detection and forwarding. But first of all, we'll just take a look at adding it to the IA model, and then I can take some questions. Nope. So I got another minute or so here to build. But as it's building, does anyone have any questions? Yes, yes. Yeah. Let me finish building it, and then, well, actually, I'll start finding it right now. So let's see, demo project. Go work. Let's see. I did generate the RTL earlier. So I'm going to do CA RTA. Let's see. There we go. See, what do we want to show? Here's the ALU. If you wanted to take, we could take a look at. Yeah. Oh, the top level? Yeah. This one right here? So here's the top level. But if we take a look at the ALU one, and this is what Barath was talking about before, you can see where it clearly indicates exactly where that line of RTL came from. So it says like it came from CA pipeline 3 execute stage and on line 135. So it's really easy to go backwards, right? So if you happen to want to understand, you're looking at your RTL, you want to, where did it come from? You can go backwards, and we'll actually. So that's a really key functionality is the comments that it gets generated. So my IA model is done. So let's go back to my core mark. I'm going to clean it, so I can make sure I'm going to use my latest compiler. I'm going to say build. And if I look at the, disassembly, I think I just called it Mac. So you can see that I've added a Mac, right? I've now using 3 input registers and 1 output register, so I added an additional resource. Now to go to the next level, I could actually implement it in the CA model, but before I do that, because like I say, I have to, it's a little bit more complicated, but not much more complicated because I do have to add data hazard detection and forwarding. So before I do that, does anyone have any questions? Now I should say, do you want to see me do data hazard detection? It's not that difficult. It just takes making sure I type it in correctly. So I will actually do that unless someone has questions or wants me to do something different. So let's take a look at actually adding the Mac now in the CA model. So once again, the steps are the same. No matter what my instruction is, it's really the same. So I need to go back and add a microcode opcode for that operation. So what I'm going to do is in my, let's see, my design, I go back to my microcode opcode for my multiply compute element. I'm going to call it a Mac. Now, if you notice, I have 3 microcode opcodes now, which means I need at least 2 bits to define my multiply my microcode opcode. I don't have to go anywhere to change it because it will automatically bit size correctly to the number of bits that I have in my microcode. Now, let's go now to the next level. That's the first thing you do. So the next thing I have to do is I actually have to add that instruction in 2 minutes. Oh, okay. Well, I don't have time, but that would be like another 5 or 10 minutes to do. But I appreciate everyone coming out here. I can hang out here or over here or at the Codasip booth at the end of the hall. But I got 1 minute. A couple questions or? Well, thank you for your time, everyone.